Strip away the stars and you'd find a hidden sphere 10 times heavier. That sphere is a dark matter halo, the scaffold gripping your galaxy. The immediate takeaway is simple: galaxies live in invisible cocoons. Picture a city at night, wrapped by a quiet ring road. Cars move smoothly because the ring guides traffic without being seen. A halo plays that role for stars, gas, and dust. Dark matter means matter that doesn't glow, but still has gravity. It outweighs normal stuff by roughly 5 to 1 on average. Gravity from the halo steadies rotation and seeds structure during growth. We spot it indirectly by how galaxies spin and bend light. By the end, you'll see the hidden skeleton shaping the cosmos. Bottom line, the unseen scaffold is real, and it runs the show. Zoom out from the Milky Way, its thin disk floats in darkness. A dark matter halo is a spherical cloud of invisible mass. It surrounds the galaxy and anchors everything that glows inside. Without it, the outer stars would drift away fast. Gravity from the halo deepens the well, so orbits stay bound. The stuff inside the halo formed early, then kept merging. Small clumps collided and built a larger, smoother envelope. Cold dark matter moves slowly, so it piles up efficiently. Gas fell into that well, cooled, and spun into a disk. Stars formed from that disk, then kept tracing stable paths. Rule of thumb: the halo sets the map, the disk paints roads. The density is highest near the center and fades outward. Simulations predict a gentle cusp near the core with long tails. Particles pass through one another because they rarely collide directly. They still share gravity, which sculpts a mostly round shape. Our home shows the scale in clean numbers. The Milky Way's halo likely weighs 1 to 2 trillion suns. Its stars add up to about 60 billion suns, so the halo is roughly 20 times heavier than the stars. The halo stretches nearly 200,000 light-years across. Our bright disk is only a quarter of that size. Satellite galaxies orbit on long loops within this bubble. Their paths wobble as they feel clumps inside the halo. Net result: the halo is the quiet boss of the system. Under a cold night sky, a radio dish listens to spinning gas. A rotation curve is orbital speed measured versus distance from the center. It tells you how fast stars and gas circle at each radius. This matters because speed reveals how much mass sits inside the orbit. If mass were only in the bright disk, speeds would fall outward. Like planets around the sun, velocity would drop with distance. Instead, astronomers saw the opposite pattern: shockingly flat lines. Gas kept whipping around at nearly the same speed far out. That means extra mass keeps adding up with radius unseen. Dark matter fills the gap and stretches well beyond the starlight. Mechanically, gravity pulls harder than visible matter alone can explain. The curve stays high because the halo's mass keeps dominating. Example in real terms: look at galaxy NGC 3198. Its gas circles near 200 kilometers per second for 30 kiloparsecs. That distance is about 100,000 light-years from the center. The speed stays steady there, which screams hidden mass. Tiny test: imagine turning off the halo for a second. The outer gas would slow and the disk would shear apart. So the picture is: flat curves point straight at a heavy halo. Now stare at a galaxy behind a cluster. Its light stretches into arcs. Gravitational lensing is light bending around mass, like glass warping images. It matters because bent paths reveal how much mass sits there. Light follows the curved spacetime, so geometry encodes the weight. Strong lensing makes bright arcs and complete rings around dense centers. Weak lensing is subtler. Small shape stretches across many faint galaxies. Stack enough shapes and a mass map appears from the shear. This lets us draw halos, even where no stars glow. Mechanically, the deflection angle scales with mass along the line. Measure the stretch, and you can weigh what you cannot see. Here is a striking case with clear numbers. Abell 1689 acts like a cosmic magnifying glass. Its mass is hundreds of trillions of suns by lensing fits. Background galaxies appear as long blue arcs wrapped around its core. The brightest arc spans several arcseconds, which signals a deep potential. Overlay the stars and gas, and the mass still stretches wider. Bottom line, lensing sketches the halo directly, pixel by pixel. 6 billion light-years away, filaments thread space like glowing rivers. The cosmic web is a vast network of matter linking galaxies. It matters because these threads deliver fuel and set traffic lanes. Dark matter forms the bones, while gas flows along the lines. Gravity pulls material into filaments and then into nodes at crossings. Halos grow where multiple streams meet, feeding galaxies for gigayears. Torque from asymmetric inflow can set a galaxy's spin direction. Cold streams can punch through hot halos, especially in younger universes. Simulations show long tendrils stretching tens of megaparsecs across space. Observations now catch their faint glow in ultraviolet and hydrogen light. For example, the Slug Nebula spans nearly 1,000,000 light-years. It wraps a quasar and lights up the cosmic pipeline. Closer to home, galaxies in filaments align their spins modestly. Counts show coherence over tens of millions of light-years. So the web is not scenery, it is the supply chain. One-sentence recap: filaments feed halos, and halos feed galaxies. On a long exposure image, thin star rivers wrap the galaxy. A stellar halo is a faint cloud of old stars around disks. It matters because those stars are archaeological layers and dynamical test masses. Tidal forces shred small galaxies, then spill stars into looping streams. Those streams trace past orbits and reveal lumps in the halo. Mechanically, a passing dark clump tugs out a gap in a stream. The torn section shifts slightly, leaving a measurable kink. Measure many kinks and you infer how clumpy the halo is. Here is a number you can picture. The Sagittarius stream circles the Milky Way over 100 kiloparsecs. That is more than 300,000 light-years of scattered stars. Another stream named GD-1 shows a sharp gap. The gap is dozens of light-years wide and offset. Models suggest a dark subhalo with a few million suns caused it. This technique weighs the unseen, using stars as test particles. Bottom line, streams are seismographs for the galaxy's hidden interior. Drop into a barred spiral's heart, where lanes of stars cross straight. A bar is an elongated swarm of stars across the center. It matters because bars move angular momentum and channel gas inward. They act like conveyors while the disk exchanges energy at resonances. Spiral arms are not fixed material, they are wave patterns in stars. Overdensities rotate, and stars move in and out of them. Gas piles up in the arms, then ignites bright newborn clusters. Mechanically, resonances near corotation trap orbits and support the bar. Torques from the bar drive gas toward the nucleus efficiently. That inflow can fuel starbursts or wake the central black hole. Numbers make this vivid in our home galaxy. The Milky Way's bar spans about 5,000 parsecs across. It rotates roughly once every 100 million years, give or take. Gas streams along dust lanes, then slams toward the inner ring. Star formation lights rings near 1 kiloparsec from center. Net result: hidden traffic rules organize chaos and shape long-term flow. Pull back to see a faint, hazy sphere around the disk. The circumgalactic medium is hot, diffuse gas surrounding a galaxy. It matters because most galactic baryons probably live in that halo. Winds from supernovae and black holes heat and stir this reservoir. Magnetic fields thread the gas and help guide charged particles. Cosmic rays push on the gas and add pressure support. Together they slow inflow and regulate fresh star formation. They also keep metals circulating instead of escaping forever. Observations detect this halo and absorption against background quasars. They also map Faraday rotation, which tracks magnetic field strength. Here are touchstone values for the Milky Way. The CGM likely holds near 100 billion solar masses of gas. Temperatures hover near 1 million Kelvin over huge volumes. Fields measure at microgauss scales, faint yet effective on big scales. Outflows blow bubbles tens of thousands of light-years tall above us. So the picture is, the gaseous halo cushions and moderates the galaxy. Between giant galaxies in a cluster, hot plasma glows like ember fog. A galaxy cluster is a massive bound city of many galaxies. The intracluster medium is the searing gas that fills its space. This matters because clusters amplify the same hidden scaffolding at scale. Dark matter halos of galaxies sit inside an even bigger halo. Gravity there is enormous, so gas is heated to tens of millions. X-ray light reveals that furnace and outlines the deep potential well. The Sunyaev-Zel'dovich effect also marks the hot electrons against the microwave background. Mechanically, merging clusters let components separate by their properties. Gas slams, slows, and lags while dark matter passes through, still leading. Lensing then shows the mass peaks offset from the X-ray glow. Here is a clear numeric portrait to hold. The Coma Cluster weighs around a quadrillion suns by several methods. Its plasma stretches millions of light-years across the core. Strong and weak lensing both confirm a dominant dark halo. Bottom line, at cluster scales, the skeleton grows colossal and undeniable. We started by peeling back starlight and finding a heavier sphere. Now you have seen its tracks in curves, arcs, and streams. You watched filaments feed halos, and halos feed the disks. You saw bars guide traffic, while magnetic halos set the weather. You scaled up to clusters where the same rules still apply. Across it all, gravity pulls on more than meets the eye. That unseen mass doesn't just hold galaxies together, it choreographs their lives. One gentle ask, join me for the next deep dive by subscribing. Not urgent, just a tap so these cosmic stories find you. Until then, look up and remember the quiet scaffold around everything.